Hello everyone, so it's 1 p.m. now, so welcome back. So we'll start this afternoon session.
How we go from zero to some kind of capability.
Welcome back. So for this afternoon session, so our first session is PNNL WSU research highlights. So we invited distinguished speakers from both PNNL and WSU to introduce some important research at both organizations. So we have 4 speakers. Our first speaker is Natalie Boyson. She is the chief scientist at PNNL, and she will talk about the PNNL initiative called Grid Operations, Decarbonization, Environmental and Energy Equity Platform. And our second speaker is Thomas Edgar from PNNL. He is a cybersecurity research scientist, and he will talk about another PNNL initiative called Resilience Through Data-Driven Intelligently Designed Control, RD2C initiative. And then we have 2 speakers from WSU. The first one is our co-director, Namika Dubey, and she will talk about grid edge modeling and coordination to support decarbonization and resilience. And our second WSU speaker is Saeed Lotfi Fard. He is an associate professor at WSU, and he will talk about protection, stability, and control with IBR-dominated power grids. So please sit front, and we will start our session.
One. Test 1, test 2. All right. Thanks a lot, everyone, and thanks a lot for the opportunity to talk right after lunch. So I know you're all good on caffeine right now with your sodas. It's my pleasure to talk about GoDeep. This is a lab agile investment over the last 3 years with over 40 people working daily on it. So it's my pleasure to talk a little bit about it with recognizing my colleague, but also the entire team. As part of this entire team, we're talking about decarbonization, climate, and equity. As we talk about decarbonization, we are following regulatory goals, which are extremely aggressive, and let's put it not aggressive, but optimistic, I heard this morning, and also in the face of climate change. So to address those goals, we had to change, those are driving a number of different questions. This is a slide that you saw also from Dave this morning. We have the utilities, we have states, we have communities all asking questions about what and where those energy transitions are going to interact with them. They are all our neighbors out there. Those are all the questions that we have. And if we want to address them, we have to break ground on a couple of science and technical challenges. If you step back a little bit on how we're going to address those goals from an energy perspective, and everybody who is involved, we kind of look at, from a very academic perspective, how the long-term planning is being performed. We have, and you start from the left side, this is where the goals are typically being defined with a number of assumptions on the technology. So think about here on the left side, defining those scenarios and those decarbonization pathways. How are you going to derive those incentives and provide more money or grants for hydrogens or for carbon sequestration or for a certain type of electrification of transport? This is kind of that state that is very high level and very regulatory. So this is where we interact with the states and the communities. The second step is going to make it, how do we get there? So this is where we start having these expansions and we cite this infrastructure. When we cite this infrastructure, this is where we start talking with a lot of the investors, the different public-owned and privately-owned utilities. This is where it's going to impact the consumer rates. So we also get a lot of concerned scientists, the disadvantaged communities to understand where are those plants going to be. And then you have the one on the right. It's operation and planning. We're talking here about a decarbonized grid. Are we going to have the same operations tomorrow that we will have today? And what is going to be also, again, impacts on the rates? How are you going to coordinate across regions? And what will be the resilience to climate change? So to address this, we work on three specific aspects in this initiative. The first one, where we had to break ground, is on the modular modeling platform. What we mean there is that in that previous slides, I mentioned that we talked to a lot of people. And all of those people are going help from the labs, from consultants, from other agencies, and they all use different climates. They all use different sources of social science and different questions. So we do need somewhere an end-to-end workflows where maybe there will be some inconsistent recommendations across all of those stakeholders. But we need to understand if those inconsistent recommendations, are they inconsistent just because of the design of the policies, or this is because of our models and different assumptions that we could have a consensus on. The second one was on relevant climate and social science product. As it was mentioned this morning, we are going and we are targeting a lot of the extreme events. But the grid of today is not the grid of tomorrow. What are the opportunities that we should know from climate today that maybe are being addressed by market, but are not going to be addressed only by market in the next power grid? And we're talking also about the impact on our neighbors, on the social science. It's a major change. So how do we know that it's going to be adopted? So we also do understand and really get more social science metrics consistent of our speakers. So we're going to talk about that. And the last one is dissemination. We're talking today earlier at our table. That was a great discussion where we have all of those data sets, all those science, we have publications and tools. As scientists and engineers, we're very proud. Yeah, but how do we get to some decision making, and how do we get all of this information to all the people we are targeting? So I'll accelerate a little bit. Here from the platforms, this is something I had the opportunity to present to WSU twice during the presentations. Those are the different models. Those are simplified, but this is where we collaborate a lot with the different research institutes. All of those models, they are connecting. They are open source, most of them. It means that they are ready to collaborate with others. They are vetted, documented individually and together. And we also have been learning in terms of best practices, reproducible and so on. We've also been learning on defining all of the metrics that are important all the way to the end. So let me switch then to the scientific highlights. What is the research that this platform has enabled us to do? It's just a subset of the different highlights. This one is on electrification rates. We've been working on load. We've been working on what the load is today, but how to forecast and project the loads of tomorrow. Electrification of transport is a massive uncertainty in what the load is going to be. You have a lot of load projections out there right now. What we're providing here is transparency on what are the differences between those load projections. One, is it due to policy? One, is it due to different assumptions on the readiness of the future technologies like CCS, and understanding how they play. Like the first 15 years is going to be really mostly policy. After this, it's going to be more some of the technology innovation. So what does that mean for your investment? All of those rates are actually being used right now by a number of utilities and the Northwest Power Council and so on. They are being used as a benchmark because everybody's comparing their ore electrification rates. Another highlight is a slide that you already saw earlier today is about what I call climate intelligence. So those are the energy drought. Each of the circles here is the size is the number of events per year. The color is the drought durations and size, and the location is by balancing authority. What's important here is how often do you have energy droughts that are longer than 1 day? When it's under 1 day, you do it a lot, it's being managed by markets. When it's longer than a day, what is the policy in managing storage and what will be the market to ensure that we have the storage or the operations to address it. We're doing it under the future grid as well. Those ones are being addressed today. Under our projections of infrastructure and future climate, we're seeing that those energy droughts are going to be much more severe. That's energy, that's a generation and a capacity problem. So this type of information and those data sets, they are presently being used to size storage and to evaluate future transmissions and really to understand what is not a threat today, but could be a threat tomorrow. All of those data sets of coincident wind, solar, load, and hydro, they are presently power system model ready. And so we are using them to develop scenarios for reliability studies. This slide is from the National Transmission Planning Studies, being using and leveraging our data sets to say when you have a heat waves compounding with drought, what would be the value of new transmission studies. All of those data sets, we also work with the WEC to develop their reliability studies. They also had a couple of heat waves and cold snap scenarios. And we're also working with understanding during those extreme events with the FERC 896 order, understanding the transmission reliability. What are the maximum transmission transfer that you might need in the future, and you do need to have reliability for them. Another one is going to be, so this was very engineering, scientist focused and oriented. We're also looking at the equity piece of what's the impact of decarbonization on our communities. On this one, we evaluated the definition of disadvantaged community from the national scale, and we evaluated what it means, what are the local perspective of what energy equity means. On those maps, you see a different mismatch. And what it means and how this information can be used is going to be for our policymaker, for example. When you're going to have some grants from the national and the federal state, understanding who locally is going to benefit and if we can't tell which policy should do. It's kind of it's a potential use case of really understanding what are the needs on the ground compared to how they're being generalized at the national scale. Another potential use case here on decarbonizations, it impacts it's not just the energy, it's the entire economies. And so here we've been evaluating how the distribution of incomes would change by state. This Palmer ratio, that's out of my expertise. The way I understand it, you have the scales here. When it's purple, it means that your income distribution is a bit more flat. And when it's highest, you start having kind of that scales in income. And so we're seeing here the difference in that ratio associated with the decarbonization scenarios. What it means, well, we need to work more with policymakers, but this is really an index of what will be the impact decarbonizations on your economy and on your community, on your populations. And so we are working on then, what's next, how you further translate this into some of the policies that people might be interested in developing or for evaluating policy. We've been talking about communication. We have all of those data sets. We have our papers, we have our tools, they're all documented, open source. We're super proud. We put them on a very nice website, which is pretty traditional. It's an awesome website, I recommend it. You're going to find all of it. Is it enough? No. If you really want to talk to all of the stakeholders that we've been mentioning, if you already know the type of studies and analysis you want to do, we've been developing EGDIA, which is for environmental justice, and it's going to overlay all of your social equity and the different disadvantaged communities, and it's going to overlay with a number of metrics that we've done. What it means is that if you know what you want, it's the type of analytics where it's prescribed, and it will allow you to play with it and get the exact information that you need, but it's already prescribed. The other one is scrolly telling. It is exactly what it is. You've seen it in website. You scroll on your website, and it's going to tell you a story, and it's interacting. It's going to be more for people who don't know what they're after. It's going to tell you a story, and it's going to, here we have one and I have a demo on siting, and it's going to highlight what it might mean for community, for your neighbors. This new power plant is going to be there, and you still have a couple of interactive nudgets to see, to address some of the questions you may have. And then there is the last one. If you didn't fall into that first three ones, you're the one that always asks, yeah, but what about this? What about that? Have you looked at into Seattle? Yeah, but I want it for the Tri-Cities. We've been challenged. So we've been developing the Grid Copilot, which is Alexa, basically, except you can't use your voice. It's a great chat. And you can access, you can ask a lot of the questions, and it's going to get you back the answer. It's going to mine all of the data sets that we develop so that you can get answer to your exact questions, whether this is in time, in space, and so that's where, if I have time for quick demos, I haven't turned up the lights. So, take a quick run at this one. This one is the storytelling. No? Okay. All right, are we too moving the? Okay, all right, it started. So the storytelling here is telling the story about the future power grid and where, based on our scenarios, where we think that the wind and solar are going to be. We first understand where the land, where suitable land might be, so you have those maps. And then we understand the economic viability of those regions. It means that we're trying to put aside some of the farmlands and some of the different values that we can have user-specific. And then you have this nugget here. You may have some questions. Okay, it's 2050, but what if I wanted it in 2035? So it's pretty interactive in some places where you can have a couple of those questions. You can also zoom in that map. So that's for the storytelling, and we have it for a couple of questions. So we have two stories like this right now. And the last one is the Grid Copilot. Thank you. Whoever did it, thank you. So on this Grid Copilot, you have the chat on the top. You ask your question. On this one, it's a pretty static questions, but it's going to be the portfolio over the entire US for a certain year. You have the visualizations, you have the tables on the left that is providing you a summary, and sometimes you have questions about the transition period. All of the questions from the industry are sometimes not just about 2035, but the way to 2035. So we're getting those time series here that provides you some simulations. All of the data that are being used by that visualizations is then also accessible, and all of the data is being cited, and all of the request, it's also making sure that it's reproducible. It's also being provided. That's it. Thank you.
Testing. Can everybody hear me still? Hello, everybody. I'm Thomas Edgar. I'm a Chief Cybersecurity Scientist at PNNL, and I'm going to be talking to you about the Resilience Through Data-Driven Intelligently Designed Control Initiative, also known as RD2C. So the major objective of this initiative is to kind of take a step back. As we know that these environments are a lot of our operational technology and control environments are continuing to digitize and to use more and more of the communication infrastructure to operate. We're aware that this is really starting to increase the attack surface and the potential for cyber-based risks to cause these systems to have challenges. And so taking that perspective, we really want to step back and say, okay, we know we're going to have problems with these. We know that there's threats out there that want to take advantage of these capabilities. So can we redesign the controls and develop new controls that are resilient to this perspective and actually be able to fight through these types of events so that we can be resilient and persist even under adverse conditions? Under this initiative, we've got two major questions that we want to answer. One is, do we really know all of the emergent and ensemble activities that are going to go on as we start to increase more and more of this, more of the edge control, more of the communication-based dependencies? Do we fully understand all of the ways that these systems can emerge and cause new behaviors? And so that we don't think we do. And so one of the questions we want to answer is, what are all those behaviors? Can we get ahead of this problem and start to understand where, as we design these systems, how they're going to behave and how we should better design them? And that's the second piece. Taking that knowledge, can we create these new controls? Can we create these new architectures to withstand and be better designed to be resilient to some of these fault conditions that we expect, or these adversaries that we know will target these systems? And so I'm not expecting you to read all of that capability, but there's really three things, three kind of major outcomes that we're hoping to achieve in this initiative. The first is, how do we even build these systems? We want to be able to have a controlled environment where we can experiment and study the problem and make sure we have understanding from the data that's coming out of it. And so how do we build these systems, and how do we do the experiments to get that confidence in the results of the tests that we're doing, especially when we're looking at newer systems. I forgot to mention the use case we're really focused on here. While we want this to be general across all cyber-physical systems, we're focused on distribution systems with higher penetration of DER, specifically inverter-based resources, and with integrated microgrids in them. But as we're looking at these future test cases that we don't necessarily have today, how do we build out the environments, and how do we make sure that the data and the validity of the things that we're looking at are accurate to inform our decisions? The second one is really to build out those new control structures. So what are the new control approaches when we step back and look at it from this perspective that we should be investing in and developing? And so building out new approaches that we can start leveraging for these resilient designs. And then finally, it's bringing those two capabilities together to actually validate these things. We really want to be able to not just say we are doing something resilient, we want to actually show that we're doing something resilient. So putting these new controls into a controlled environment and running through a series of tests so that we can actually show empirically that we are moving the needle on resilience. So the approach that we're taking on the top of this picture, we're looking at controls and mitigations across multiple layers. So the first on the left is at the device level, looking at primary controls at the device level to be fast-acting response. So everything from advanced grid forming controls, which I know Wei has already been successful to transition to some of our DUE programs, all the way to stuff like peer-to-peer distributed control, where if you lose your kind of secondary control, your SCADA, let the devices work together to try to persist without the higher control that we're used to. The second one that in the picture is the cyber layer. So let's not just think of the cyber layer as a risk that we need to handle, but also take advantage of the cyber layer. And so the second mitigation that we're really focused on is leveraging a middleware capability to inform the applications of the current state of the cyber layer and the risk potential that we're seeing and the potential attack activity, so that the controls can change their profile and actually decide on how to respond to the different conditions that they're seeing. And also leverage the resiliency in the cyber layer itself to support the control actions in providing the resilience. And then the final is at the application layer, the secondary control, and creating capabilities to make sure we're meeting constraints and still providing our objective as much as possible while enabling this resilient response. And on the bottom of this picture, we're really focused on two capabilities for testing and validation. So one capability that we're really focused on is co-simulation platform, where we can actually use models and simulation environments to quickly iterate through a number of test cases and look at things like co-design to better understand and do quick tests on some of these capabilities and validate that we're initially seeing the response that we want. And we've already done some open source releases on some of these tools. So there's a tool on our GitHub called Natig, which is kind of an advancement of some of the Helix co-simulation capabilities, if you're familiar with that. So take a look at our GitHub page for some of the capabilities we've already released. But taking it a step farther, we really want to be able to drive and validate these things to a technology readiness level that industry and vendors are willing to uptake them. And so we really need to be able to prove in realistic conditions that we're achieving the objectives and we're not causing additional problem. And so we're really working extensively on hardware-in-the-loop test beds and high-fidelity models and simulation capabilities so that we can test these things in realistic environments and build out realistic models at the levels that we need to prove to industry and to the vendors that we are achieving the goals that we want. On that capability, we're really working extensively with OpenRT. To date, most of our models have been focused on smaller stuff like the IEEE 123 node test feeder, but we are pushing the bounds and working with Opal to scale and make these things more efficient. And so we're building up to things like the 9500 node test feeder with high fidelity models that can show all the dynamics that you would expect to see with some of these inverter-based systems. So there's a number of capabilities we're hoping to get out of this. So the first one, I'll start on the top left, cost prediction. So one of the questions that we really want to be able to answer for a lot of our sponsors is, what could go wrong here? We'll help them answer the questions of, if you have this type of system, what could go wrong if you see these types of events? And so a lot of our simulation capabilities and our modeling and test bed capabilities, we're really building towards that capability to help some of our sponsors answer those cost prediction questions. As I mentioned, we really want to be able to say that we move the needle empirically, so building out the approach and the processes and the techniques and the metrics for understanding resilience under the terms that we're talking about. And so really building out those frameworks so that we know how to measure and how to quantify resilience and generate data sets for that. One of the things that we're looking at is the threats too, right? We need to be able to model the threat tactics and techniques that you might want to see. And so how do we model those things accurately enough and with enough fidelity so that we can answer these questions? We're not specifically tying into any specific threats, just generally how people might attack these systems and what that would look like so that we are able to show that we can respond and survive through some of these realistic cyber attacks. Integrated system control, so making sure we know where to put the sensors, where we should put the controls. Some of the questions like where, if you're going to deploy some new inverters, where you should put those, where should you put the resources when you're doing the design to make sure you're building the theoretically the most resilient capability to respond. As I've already mentioned multiple times, we're extensively built on, or looking at the capability to further create newer testbed capabilities to answer some of these new questions. And then finally, this resultant set of control prototypes. So I've already talked about a few of them, but the goal is to get these out there, not just have these kind of academic papers, but actually get these out there to industry and make sure that we're providing stuff that can get to the market that can actually move the needle on resilience. So this is a 5-year effort. We're coming up on our final year. The last two things that we're focused on this year is two capstone projects. The first one is really bringing together, we've done kind of piecewise validation of some of our controls. We want to bring as many of the controls together into one architecture and then put them on the most complex testbed environment that we can to really show and prove that we are improving the resilience and how much we're improving the resilience. And the second one is extending our co-simulation platform to really start helping answer some of those great questions that our sponsors have and show that we can build the platforms to help them answer their questions more efficiently. And the last thing that I'll leave you with, I've already mentioned we've released some of our tools and materials, but we intend to, I think in the first quarter of next fiscal year, do a big push for all of the tools, data sets, and models and things that we intend to release, and kind of do a real big push out of all the capabilities so that everybody can take advantage of all of the hardware that our teams are doing. That's the end of my slides. Thank you.
All right. Thanks, everyone. So I'm going to talk a bit about what my group has been working on in this particular space of grid edge modeling and optimization to support decarbonization and resiliency. And I think you might have seen this slide, the next one that's coming up before. It comes up. Okay. Right. systems used to look like. We have a very aggressive integration of distributed solar right now. This slide is showing you we have 4.2 million homes with installed solar panel as of 2024. We are seeing or expecting economy-wide electrification, including in the transportation and industrial sector, and the expected demand is to go up by 38% by 2050. This is a slide, this is a result from one of the studies done by NREL. We're also seeing a significant increase in extreme weather events and their impact on the grid. So what I'm trying to show you here is that our grid edge is transforming in significant manner, both from resource perspective as well as from the impact perspective. And what we are looking here is a system which traditionally has, I need to be a bit slow with my clicks. Right, a system which has been not actively managed before, but seeing a lot of active resources being integrated. This is distribution, this is grid edge. So lack of these active management of these resources leads to underutilized infrastructure. And the question or the research or the work that my group tries to address is that how can we leverage these resources and more actively manage them so that we can get most out of it. And one of the ways to do that is to look into what are the emerging modeling, optimization, and control challenges here to integrate all these resources together to provide a more systematic and synergistic integration into the system. So what is the problem? So, our grid requires supply-demand balance all the time, and typically the grid services are designed to meet this requirement. These are typical grid services. This is out of a PNNL report, and it very nicely, articulates what are different types of grid services and why they are different in their definition as well as how we are going to procure them. And the question we ask here, traditionally these grid services have been provided at the bulk grid level. Now we are having more and more active resources at the grid edge. So the question is, how do we unlock these grid services using the ERs, and what is really needed to solve this problem? And when we think about distribution or grid edge, we are really looking into a very large-scale system, which has significant modeling and optimization challenges. So that's one of the core questions here, that how do we manage or solve this large-scale control, optimization, and modeling problem? I'll give an example with the help of why, what we have so far from bulk grid that we know from optimizing the grid operation is not sufficient for us to work with, distribution system. So take the example of this synthetic 2000 bus power system test case. It's out of one of the Professor Tom Overby's work on developing these synthetic use cases. This 2000 bus power system test case represents almost, most of the high voltage level airport grid. If I zoom in on just that one concentrated area that you are seeing here, close to 300,000 end-use customers, 448 feeders, and 160 high-voltage buses. The mere complexity of trying to optimize this particular grid edge, which is where we are going, which is where active resources are being added, is huge. You are really looking from tens of thousands of buses to really hundreds and thousands of buses or even grid edge devices. How do we solve this problem of growing number of controllable resources? Typically, traditionally, rule-based methods, they're not sufficient because we are looking into different and more complicated types of grid services from these grid edge resources, and it needs to be integrated in a more synergistic manner. Complexity, these systems are very hard to optimize and as well as to model. So what my group works on is tries to answer some of these specific research questions. One is how to unlock grid services from DERs, and I think that's not grid, that's grid edge resources. What kinds of broader challenges are we facing, and how optimizing grid edge can help? Right. So that's one question. The second one is, what are unique modeling and optimization challenges that require developing specialized algorithms for distribution system? So I'll give an example of modeling challenge. We are talking about energy efficient buildings. Buildings are one of the loads. Loads are typically represented in power system model as PQ loads. We're talking about these dispatchable loads at the building level, which have thermal dynamics within it. Now, if you really want to model the entire building and the entire process that goes inside the building in terms of energy consumption in grid models, it won't solve and it won't really give you the results in the time domain you're looking for. So there is this question about how do we develop realistic or simplified model, but not too simplified, or useful model for the grid, for these grid edge resources that then can be used to answer some of these questions about unlocking grid services. Then the next step of the problem is, what about planning problems? How and where to strategize to maximize their value proposition and value from different perspectives, from resiliency, from efficiency, and from other end use values or end use loads perspective. And finally, when do traditional optimization and control methods are insufficient? And when do we truly need machine learning or some advanced approaches? And how do we really develop them specifically for power systems need, not just run-of-the-mill AI ML that has been developed right now? So what are some unique challenges there? How do we build physics systematically in those models so that we are able to answer some of these questions and moving forward? So with that, one of the technical challenges that my lab works on is this scalable modeling and optimization, and how do we look into this from while we are answering some of these use cases. This is just a slide, I'm not going to talk much about it, but really what we're looking into is, traditionally we are looking into an optimization problem. Optimization problem has been solved in power systems forever since the grid has been really realized. But what we're looking right now is we have these added challenges because of non-linearities which are introduced because of grid edge resources or even the system model itself. We're also looking into significant sources of uncertainties being introduced in the network, and we are looking into a stochastic version of these problems that have to be solved not just for planning but also for operations and for real-time response as well. So our work in this domain, we have been able to develop some computationally tractable algorithms which work in a centralized manner using approximation and relaxation techniques to really address some of the scalability challenge. We have been also able to address the scalability through decomposition or problem decomposition, looking into more distributed versions of the problem and how do we really solve this problem in a cohesive manner so that you can get the answer in both for planning as well as for the operational time domain. One of the lacking at the distribution level at least is benchmarking of these different algorithms that are coming up. So we have started to do some work there and how to benchmark these algorithms that are so many scientists and so many researchers are developing. What is a good platform for everyone to come together and say that, hey, this is my algorithm. How does it compare? And where does, what are the benefits and some of the challenges? Then we also started to look a little bit into learning for control, specifically reinforcement learning algorithms, and looking into how they can be integrated for grid edge decision making. And we started with a very vanilla version of that without any physics, just learning through the models and scenarios. But then we started to advance it a bit by incorporating specific physics-based constraints and how that can be used to inform some of these learning-based decisions. And finally, my slides are moving faster than me. Sorry. Finally, we are also looking into solutions to ensure safety, as I mentioned before, because we are looking into safety critical system. Whenever we think about machine learning based methods, one of the questions is what is the surety that these solutions are actually safe for physics-based operation of physics-based systems. So we're starting to look into how to systematically embed that safety in our solutions and what are some approaches to do that. One thing I want to highlight here is that it's our learning over years that algorithms that leverage domain knowledge are shown to improve performance, and we have seen it systematically as we have developed these algorithms. Okay, so I want to highlight across all these work that we have been doing, my collaboration with PNNL in terms of this optimization of grid edge resources and integration to support decision making at the distribution level. I have been fortunate to be a part of several PNL-led projects as well as industry-led projects where I collaborated with PNL scientists as well as our industry stakeholders here to actually see the value of some of those solutions and learn through them, that where what I'm thinking is not right or how this could be improved further to really, really impart the impact that will get these algorithms out there and not just on research papers. So these are just highlights of some. A brief summary of these projects is these algorithms for edge, integration. They are our algorithm started with more centralized understanding of the network operation, and it's moving more and more towards distributed and decentralized operations. So we developed some of these algorithms through these projects, and now we are in a stage of actually doing field demonstration of some of these algorithms in actual utility distribution system. Two of the examples here are DOE Connected Community Project, where we are subcontracted through Avista and collaborating with PNL on developing this distributed grid edge coordination towards providing grid service, specifically for building flexibility, as well as, see, it's again moving faster than me. And the second one is DOE EI, and we are working with Comet on this one to work on providing resiliency support solutions and using distributed solar and PV to provide restoration and recovery in the aftermath of an event. All right, okay. So finally, I want to highlight one of this effort that we started for the benchmarking study. My group and some of my past students who have now graduated and moved to PNNL, they are research scientists there. We started basically developing this Python-based distribution optimal power flow test bed. We call it dystopia, which is basically dystopia, but we don't see it like that. OPF, and our goal is to basically, provide a simple toolbox to the community to say that you don't have to reprogram and rewrite every power flow algorithm and optimization algorithm to really solve and test your amazing analytical method or amazing optimization method or amazing machine learning method. You don't have to do that. You can just come with that as a module, and we are going to provide you basically in this toolbox example test feeder cases, example power flow algorithm buildups, and you can just use your algorithm to see how does it perform in this particular toolbox. And we think that this can actually help accelerate development of optimization algorithm as well as benchmarking and testing of it. We have started to do this. This is we currently have mostly implemented three unbalanced linear power flow and optimal power flow algorithms, but we have been able to benchmark it across for simple optimal power flow to mixed integer problems to also multi-time period problems with battery storage optimization, and now we are moving towards the stochastic optimization for planning as well. So we are building this particular toolbox to basic elements of optimal power flow or grid optimization and learning toolkit so that someone can basically come up with their algorithm and just embed here in this particular platform and develop it, test it, and benchmark it. So if you want to learn more about it, I would direct you to Rabayat and Nathan. They're sitting there. They can tell you more about it. We do have a tutorial on this particular toolbox accepted for upcoming Grid Edge conference from Power Energy Society in January, and we're talking more about this particular toolbox. So this just highlights how we keep on, how this collaboration with PNL, university, industry stakeholder truly helps to develop these research products and algorithms beyond paper to real world. We are inviting contributions to develop, test, and benchmark new algorithms. We are specifically interested in nonlinear algorithms. If you have any kind of nonlinear optimization algorithm or machine learning algorithms, we would love to hear more from you and talk to more about it. Okay, so I'm still on time. We have, of course, growing complexity of grid operations, and scalable simulation optimization is key to study and operate complex power grid. We are looking into changing nature and requirement of grid at the edge. We need to have scalability across interconnected T&D system and really truly distributed solutions to really solve this problem. And eventually, we are looking into complexity, specifically as we get into climate resiliency solution, extreme weather event solutions, and start to think about planning for longer time horizon with significant sources of uncertainty. How do we solve them? How do we really get these out of those algorithms that we are producing to say that, hey, this particular solution looks like, and these are the values and risks associated with this particular process. Are really doing distributed and parallel computing, domain-specific approximations, and building up more on physics-informed learning in this particular area. I do want to acknowledge my research group. These are all the happy students who I have, who are currently a part of my group. This is a picture from last week. So we're just kicking off the new semester. I want to also acknowledge all the students who have graduated. They are doing great where they are, and they still keep in touch. See, again is running faster than me. And I do want to acknowledge the sponsors for funding and for supporting all the work and for teaching us how to really impart impact for things that we keep on developing. Thanks everyone, and I'm on time.
Thank you, My name is Saidot Pipard. I'm an associate professor at Washington State University. Professor, thank you, Anamika and Meidu, for giving me the chance to talk about some of our ongoing projects. So, basically, in my group, we are working on the protection, stability, and control of the IBR interconnected power system. So the challenges that we are looking at are the new dynamics and new fault characteristics that IBR causes in the system. And we have seen that in so many recent events that cause the major power outages. It can be, basically it has happened in all over the world. It has happened in the UK, Australia, China, Germany, so many states in the US, including Southern California, Texas, and so many other places. So every few months you see some of the NEC event report come out. So and you see that so many issues, mainly you can categorize because of the new dynamics and new fault response characteristics that IBR causes. So the needs are, we need the tools and methods for more informed and reliable interconnection of the IBR. So the solution that we are working on that, we are working on the developing methods and tools for analysis, modeling, and monitoring and improvement of the fault resilience of the system. So basically the goal is that we come up with some fault resilience IBR dominated power grid. So for the sake of time, I picked a few topics and a few projects that we have extensively worked on in the last several years. So please do reach out if you are interested to have more discussion on these certain projects. And of course, we can find mutual interest for other projects as well. So one of them is that, especially for PNNL, being well equipped with the simulation and co-simulation platform, is the protection system and IBR connection studies. So basically, how to do the co-simulation of these tools. So co-simulation of the protection systems and power system dynamics. For example, a few years back, we did the co-simulation of the PSSE and K. And we applied that to the 20,000 plus wave system to study that how the event propagated when we model the detailed model of protection system compared to the present practice that totally ignored the dynamic of the, not totally, but just very few, and also the way they model, that's how much detail you integrate, that's totally different. So the study that, for example, we had in that, the result that we had, so for example, here you see that we model the event between Oregon and California, including the RAS schemes and different type of protection system, even happen in that timeline between these two states. And if you don't model the protection system, everything looks fine. But if you include this co-simulation of that one, you see that because of the event in this area, sub-protection function in Denver, Colorado, operate and causes the propagation of the event. So you see that that's how the events are correlated, so which we cannot observe if we don't model the protection system properly. And if you go to the IBR system, especially with new standard IEEE 2800, the things become more complicated because you have to go to the negative sequence of the IBRs, considering the dynamic of IBRs, dynamic of the system, and protection system as well. So that's a very challenging problem. Right now we are working on this one. So how to make sure that the standard is met and so many other operational security of the system are met as well. So that's different aspects of the interaction of protection and IBRs. So along the same line of thought, so the grid synchronization and stability is another issue. So let's assume you have an event in the system and take the line out. So how to make sure that the event does not propagate further in the system. So I picked up, for example, two examples that we have worked on that one. For example, this event happened in 2017 in Arizona, first solar power plant in Arizona. So they even happen, the protectively operated line goes out, the strength of system reduces suddenly. Then the IBRs start oscillating and they have to disconnect the system. So in that specific scenario, that was the grid following inverter. But we have shown that similar scenarios may happen even in the grid forming inverter as well. So the idea is that basically this idea, we are working in 6-7 years, maybe more, 2016 timeframe, we started working on this idea that if I have an industry practice controller, how I can provide the supplementary controller to the IBR controller. We don't want to touch the controller because we can redesign controller, but there are so many advantages of the existing controller. The industry may not want to replace the controller. But then we said that how we can provide a supplementary controller to the existing one that should be attractive for the industry practices to overcome some of the challenges. And they have done apply to, there are several papers we have published and we have done in several applications, microgrid application, big grid system application, normal system application. And for example, here I am reporting one scenario that's similar to the solar, first solar power in Arizona. So we have this system, it's working as a strong grid, normal grid, not necessarily a strong grid. Okay? Because of the protection function, some of the line goes out, the system goes to the big grid. Then the system starts oscillating and becomes unstable. Then we have applied our supplementary controller and we have demonstrated how we can overcome that challenge. The detail of the paper we can discuss offline. Then another challenge again, it comes to the same problem of how the protection and control function should be assessed from the stability point of view. So usually, especially when we work in the power area, we have the thinking of the CISO type of control design, single input, single output controller design. But again, we have shown that this is well reported in the literature that there are some scenarios that you cannot think of CISO. You have to go to MIMO, multi-input, multi-output control design. Then we have shown that there are so many issues that still is not well known in design of this controller. We will publish few papers, it's ongoing activity, but we have shown there are so many interesting phenomena you can only capture by MIMO way of thinking of the controller and interaction between how the internal logic of the protection logic of inverter are included in your study. If you don't include that one, you don't see phenomena, especially MIMO design. But the last part of the thinking I was saying that maybe that's interesting to this community also is again, related to this one is more related to distribution system. So this one, I think in my group, we are working more than last year. So if you have a distribution system, how to do fault analysis in the distribution system? Different aspects. So that is an example that we have picked up is how to do the fault location identification and responses in the system. So the issue here is that you have to balance out two problems. One is that you have extra data in distribution system. So you have mixed data sets. So you have so many data, you have multi-source data set. You have and they have different accuracy and they have different applications. For example, you may have micro PMU, they are synchronized data. You have power quality data, they are not synchronous data. You have and at the same time, you have heterogeneous data. You have analog data, which we call it the oscillatory signals, and we have a status data, so basically digital data. So then the question is that how you combine all of these data together to come up with a solution that I think I'm right on the time. So thank you. So the question is that how to combine these two, and it requires developing new tools. Because, for example, traditional fault location in power system, they work based on the substation data, and usually they are not synchronized, and usually they are oscillatory signal, analog signal. But then you have, if you have data out of the terms of the substation data, the question is that how do you combine them with your algorithm? So that's, if you really think about that, it's a complex problem. It took us so many times to figure it out what to do. Then at the same time, you have more data, but still data is not comparable with the transmission line solution. So especially, still you have partially observable system from the fault analysis. So then the question is that how do you balance out all of these things? So you come up with a solution that can take advantage of more data, at the same time it still works with the legacy system that is you have less amount of data. So then they combine these two when you have IBR interconnection into distribution system. So they have their own problem as well. So they bring in bidirectional power flow, injection, so many challenges. So that is really complex issue if you really look at that one. So then the question is that how to address this thing. So these are some of the main problems that maybe is interesting to you guys. So we can discuss that further. And this is my contact information. If you're interested in further studies, always I'm happy to discuss. Thank you. I leave my 2 minutes to you.
Oh, thanks to all the panelists for their interesting and important projects. I really learned a lot from all the presentations. So now we are open to questions. So anyone have any questions, please feel free to ask. And all the speakers are here and they're happy to address your questions.
I might just on that last one, actually, that was excellent, by the way. It's interesting. In the Northwest, we have a lot of, well, traditionally, we've had a lot of inertia-based generation, obviously, as we are slowly bringing on more and more that is not so much that way. Knowing that tipping point is kind of an interesting spot. I've been around long enough to watch it slowly get integrated, but is that something you're looking at kind of in our area of the country, and where do we think that tipping point is, if you can pinpoint it?
Yeah, that is actually an interesting study. We have as you may know that WSU is part of the PSEC, Power System Engineering Research Center. We have one ongoing project. Actually, we look at that when we say that what phenomena may happen at different penetration of the IPRs. One of the problems we are looking at that exactly the problem that you are saying that if you look at different aspects, one of them is inertia issue. So, and they say that because certain, for example, protection function, if you go to less than certain penetration level, you don't see that problem. So therefore the question is that how do you define that tipping point in which respect? So yeah, that's one of the challenges. Yeah, that's a very interesting problem you're working on.
Just a little bit of comment. Thank you, Mike, for asking this question. That story is a very important question. WSU did some amazing work here, and PLI has also done some work. You will see that in my session. Other questions?
Yeah, since you're a panel of PNNL and WSU, let me ask an AGI question. So AGI has a new strategy plan. It's got 3 elements. How does this work come together to advance the strategy plan and those 3 elements?
I can start and then you can chime in. So a lot of work that we have presented here are kind of very much aligned with those 3 R&D areas, including grid edge, power electronics, climate, and resiliency to all hazard scenario. So our goal was, when we put together this panel, was to really bring up and present what are some of the ongoing work that's going on in this area at both WSU and PNL. And basically, we saw that there is already a lot of synergy. So a lot of work that I did in Grid Edge was already in collaboration with PNL, working with on Grid Apps T and GDTAF, which is the communication project. And a lot of things that was working on the Grid Edge side with my group was aligned with that. And we were looking into how to expand that to the other 2 strategic areas as well and make it a little bit more cohesive. So Our goal is to really bring this conversation beyond this panel and develop this strategy and expand that strategy on specifically what are the complementary organizational strengths that we are bringing here and how and what we can do together to solve this problem in a faster manner rather than reinventing the wheel. So we have had some conversation during lunch as well, and I would invite other panelists to chime in here. That's how I think.
I mean, I'm not super integrated with AGI personally, but I just know that the capability and the access to the students and the professors has really helped us, and we've leveraged a lot of their expertise to progress our initiative forward. So I think that just the collaboration has made us stronger on our research.
And Thomas, that's why we bring you here.
It's the same. I had the opportunity to present on Go Deep a couple times to the group of students, and we had some excellent questions from the students. So that venue, we're talking about task force, especially from climate to grid. We have a need from both the labs, the research, and the industry on having people understanding the new challenges and the new concepts. So this is a great venue.
Yeah, basically, basically that is much beyond my thinking, but I trust Anamika, and other day I talked to him, and she has very nice plan. I hope that.
Thanks for the vote of confidence.
And tomorrow we'll have a 3-hour AGI annual review. Hopefully Anamika and I can better answer your questions tomorrow. Okay, the other questions? No? Okay.
So I'm not sure this is a well-formed question, so apologies in advance if it isn't. We talk about inverter-based resources, IBRs, but we're also coming to a world where we have inverter-based loads, like electric vehicles. So are we starting to study what that looks like?
Yeah, that is an excellent question. Yeah, exactly. So basically, when you have, because you know that some issues are a stability issue type of problems, so they mainly in the domain of IPRs, but also we have the power quality type of problems and how the harmonics can impact the grid as well. So therefore, these are another issues of the kind of power electronics based load that I can think of. So yeah, these are two areas that I'm well aware of that. But anything beyond that, at least I haven't studied that.
Yeah, just a little bit comments. I think this morning someone mentioned the data center, right? All those data center power electronics based loads. What does that mean to power grid? Need to think about that. Any other questions? Really engaging session.
So real quickly, Natalie, you talked a lot about putting together planning studies that would show how the system will respond given loads in the forecast, and which I guess shows a lot of the weakness on the system. And I guess I looked at Thomas on the cybersecurity side, which trying to protect as much as we can. But I'm not sure if we make some of that information available, the physical security is going to be really, really vulnerable. So, Natalie, what are your thoughts? And Thomas, I know you're trying to keep it all very secure, but how much of that information gets released, and do we allow that to be made available?
So the work that we've been presenting was very on the planning side. So we do, I think Judd mentioned this morning, half of the lab is about national security. So we do have a number of sponsors to which we craft some of the research to understand what are the extreme events and the threats on their different assets and operations, and then what are the opportunities moving forward. climate is not just sometimes a threat, it's also an opportunity. So this is at the research level, we are tackling, and I think your question was more on the communication. So we do work with the sponsors from a national security and perspective and regulatory. I think you've seen we've made an effort on the dissemination platform for people to understand. When people talk about climate, there is sometimes a lot of misconceptions. A couple years ago, we were hearing that climate change, a drought is climate change. No, it's different. So there are a number of nuances. So we capture at this time those different conceptions. And then in terms of statistics, kind of what is really the risk, we are going more and more moving on a new initiative here to also tackle what is uncertainty, what is risk, and how you combine them together. I think we've heard some activities on this side as well. So that is going to be some of the new frontiers for sure. But there's controls as well, different scales.
So on the security side, I would say absolutely there are sensitivities there, either from the business perspective or the system safety perspective. Purposely for our initiative, we are staying general and we're not specifically modeling any real systems to kind of alleviate some of those risks. But our goal is to build the tools that those who want to ask those questions can look at the real models and the real systems. And there's a number of government programs that look at these types of problems, and they have sharing programs with industry and ways to disseminate that information securely.
Yes, do we have any questions from online attendees? Our next session starts at 2:15, so we still have time. So, or any questions from attendees in the room?
Dr. Dubey, you talk more about like the DER integrations and the resiliency for future planning, and especially with solar. A lot of states, especially like Texas, where there is also huge contribution coming from distributed energy storage that's combined along with the co-located solar is happening both in the front of the meter and also along in the distribution side. How do you see this getting incorporated in future planning in large-scale systems? Thank you.
Excellent question. I think from grid edge perspective, flexibility is going to be the key, right? How can we ensure flexibility from these grid edge resources? And storage co-located with solar gives us that particular resource available from flexibility side. So I think probably on the home side, or residential side, the way people integrate solar plus storage is not a lot driven by planning problems, but this grid and storage or storage plus solar integrated at primary distribution or front of the meter or at community level, those are some things that we can plan for from different perspective or different utility as well as community needs. So I think that's really where this question comes up, that what are the grid services we are looking to actually extract from these resources? What is the value proposition? What are the future scenarios we are considering when we are doing this planning process? And can we quantify the uncertainty associated with that particular value proposition that we are developing for this particular resource, and the cost of really being able to extract that service, because we need, of course, control and other solutions to be able to do that. So I think this whole solution needs to be addressed to be able to make this planning process effective in actually being useful in actual system level studies, right? So we are doing some of that study. Some of those value propositions are about being able to have algorithms which can leverage these resources, but also about demonstrating the value proposition for this algorithm in real world feeder and real world systems, and being able to quantify what more can be done there, and also quantify the how much you want to control and where you want to control, where you want to invest in the control, and where it becomes too much to model and control and to invest compared to the value that you get out of that resource. So I think there are some other studies that are needed to really understand this entire spectrum of grid edge resources and the flexibility solutions from there. I hope I answered your question. Yeah.
Okay, I guess we can move to the next session.
Thank you.
Thank you everyone for thank all your speakers.